Previously, we have used Excel to plot data and to fit to a straight line. Here we want to do some behind-the-scenes work to find out how Excel determines the slope and intercept of that best fit line, as well as the r-squared value, which determines how good of a fit the straight line is. We'll take as a sample problem determining the correlation between the density and atomic radius of Nobel gases. But our real interest is in to see how Excel comes up with the numbers for the slope, the intercept, and the r-squared value. We're going to perform a shift on the data. We are going to subtract from all of our x values the average x value, and for all of our y values, the average y values. When we are subtracting the average, this is known as taking the deviation. So we enter a formula, say in cell C6, the formula equals A6 minus average, open parenthesis, a $5 colon a $10, close parenthesis. That formula will take the value at A6, one of the x values, and subtract the average of all the x values, which is A5 colon A10. The dollar signs in this formula are an example of what's known as absolute addressing. So when a formula is copied down, say from cell C6 to C7, then in the formula at the cell A6 will turn into A7, but the dollar sign will prevent this from happening. So the data point will change A6 to A7, but the range of data A5 to A10 will not change. Again, this is known as absolute addressing. And we perform the same on the atomic radii as on the densities. On the right is a plot of the original data, and on the left is a plot of the shifted data, the deviation data. Both are fit to a straight line. We see that they have the same slope and the same r-squared value, but the different y-intercept. The y-intercept of the deviation data is minus 1e minus 16. This is Excel's version of scientific notation. So that's 1 times 10 to the minus 16, a very small number. In fact, it should be 0. And it's just the computer's approximation of 0. Then it can't quite get to 0. The numbers are just approximately represented by the computer. There were no especially large numbers or small numbers in the data, and the data is not fit to an exponentially growing or decaying function. So a number this close to 0 is meant to be 0. We want our best fit to take into account all of our points, not just a few of them. A standard way to deal with all the points is to sum over them. Think of the average as a statistical measure of all the points, and it starts off by taking the sum of all the points and then dividing by the number of points. The problem with our deviations, though, is that the sum of them is 0. Again, the deviation was the difference of a point to the average, but some of them are above average and some of them below, so that when we sum over the deviations, we get 0. I've called the x deviations u and the y deviations v, and we recall that the sum of those u deviations is 0 and the sum of the v deviations is 0. So to get away from these zeros, we're going to look at the second order terms, the square of the x deviations, the square of the v deviations, and the product of the u and the v deviations. So we want to consider them, and we're going to look at their unit and their sign. Okay, so u squared is the square of the x deviations. It is positive only and has units of length squared. The v squared is positive only and has units of density squared. And u times v may be positive or negative. See that one little negative term in the list. And it has units of length times density. Again, we're doing something statistical, so we're going to sum. This time we're going to sum over those second order terms, the u squared, the v squared, the u times v. And now what do we want? We wanted a slope, and the slope is a rise over a run, and we had density on the rise and length on the run, so density over length, so we want a density over length, and this is a slope, and in general, a slope could be positive or negative. So our candidate then is uv, the sum of uv over the sum of u squared. The uv sum can be, strictly speaking, positive or negative. So that's a quality we want in our slope. And it's going to have the right units. The uv sum has length times density, but the u squared term in the denominator has length squared, and that gives us density over length. So it has the right unit and can be positive or negative. So we have Excel calculate our candidate, our uv sum divided by our u squared sum, and we see that we have indeed covered the value given to us by Excel for the fit to a straight line. Now we see how Excel got its answer for the best fit slope, what calculation it did. But now we want to understand better the question. In what sense is this the best fit slope? What does it mean by best? We will continue to work with the UV data, the deviation data, because it has the simplifying property of no y-intercept in the fit. So we have the dependent variables, the v's, and now we have a fit or a model. And so we can get an expected, we can use our formula to get an expected value. And so that's what we've done here in vfit. We've put in the formula mu, no intercept, just the slope times the u value, and done the calculation of the expected values. Our interest is in getting the best model and then asking also how good is that model. So we want to know the difference between the actual v's and our v's from the fit, vfit. And so difference means subtract. So we've here in Excel taken the difference between the data points v and the v fit from the model, the slope times the u value. You might call this an error in the model or a residual. Statistics is subtle and confusing, and so the difference between error and residual is a subtle point. If the theory is complete, if the fit is complete, meaning that we used all possible data to come up with it, then we would call it an error. And if one is expecting more data, there could be more data to come in the future, then one might call it residual. We're not going to worry too much about these fine points here. But since this data was about Nobel gases, you would ask the question to determine whether it was error or residual. Have we considered all the Nobel gases? Are there more Nobel gases than the data we have here? Again, we are doing something statistical. We want to take all of the points into account. And so our standard way of doing that is to sum over the points. But the problem with V and VFit and V minus VFit all sum to 0. So we've added another column in Excel, and we've squared what we'll call here the error, and we've taken V minus VFit, and then we've squared that. Now those are all positive, so when we sum them, they all contribute. There's no cancellation. And this is known as the sum of the square of the errors. So now we're ready to say in what way our best fit slope is best. It is the slope that minimizes the SSE, the sum of the square of the errors. And it's sometimes known as the least squares fit. It took the square error, and it's the fit that makes it least. In the middle, I've shown the calculation. M is the slope, the best fit slope, and the SSE is that last column ending with 9.7323. On either side, I've repeated the calculation of the SSE, but I've changed the slope. On the left, I've made the slope lower, and on the right, I've made the slope higher. But in both cases, the SSE went up a little bit. So meaning that the middle slope, the best fit slope, is the slope that minimizes the SSE, or is the least squares fit. I'm just going to briefly review the calculus for those who know it. The SSE is the sum over the V data minus the model, which is mu, and then we are squaring that. So we have the sum of the square of V minus m times u. We're going to take that square term and we're going to apply FOIL. So the first term is VI squared. The outside and the inside terms are going to be the same, and they're both mviui, and there are two of them, so that's the minus 2 mviui. And the last term is m squared ui squared. In calculus, we're going to take a derivative, in this case with respect to our parameter, the slope. And the first term had no m's, so it doesn't appear. A constant derivative of constant is 0. The next term is linear in m, so the derivative is just the minus 2 viui. And the last term is a square in m, so the derivative of m squared is 2m, and then the coefficient is ui squared. Now I want to take that derivative and set it equal to 0 and solve for m. This is a standard way to find a max or min in calculus. And I can do that. If I solve for m, I recover the result that we've already seen, the sum of viui divided by the sum of ui squared. Now that we've seen how Excel determines the best fit slope, let's move on to see how it determines the r squared value. Toward this end, we're going to consider two density square terms, where density squared is the unit. So one of them is the variance. So we took our original y data, we subtracted off the average y and got these v's. And then we took the square of the v, and that is known as the variance. And that term determines how spread out our density data is. And note that this has nothing to do with the model or the fit, it's just a measurement of the data itself. The other density squared term was this sum of square of errors. We took the v points and we subtracted off the fit for that point and squared that and summed that. And this was a measure of how close the data and the fit are. Let's say if the data and the fit matched exactly, then the v and the v fits would be equal and the term would be 0. If there were no correlation whatsoever between the density and atomic radius, if they had just nothing to do with each other whatsoever, then the slope, the best fit slope, would be 0, and that v fit would be 0. Remember, it was just m times u, so if m is 0, it's 0. And we would recover v squared, and in that case, the SSE and the variance would be equal. So we have these two density square terms. The variance, which is the spread of the data. It has nothing to do with the model whatsoever. And the SSE, which is about how the data and the model fit one another. The SSE tells us sort of how much is not explained by the model, hence the term error. But it has a weird unit. In this case, it's a density squared unit. But the ratio of SSE to the variance, one divided by the other, then that gets rid of this density square, and we're just left with a pure number. So we can think of it as a fraction. The fraction of the variance then is not explained by the model. Again, the SSE was error, so it's about what's not explained. And so SSE over variance is a fraction of what's not explained. So if the model is perfect, if it's all explained, we would get 0. If the model were trivial, we would get a 1, because the SSE and the variance would be equal and the division would be 1. If we further take this division and subtract it from 1, now we will get the opposite. The fraction of data then is explained by the model. Before, it was the fraction not explained by the model, but 1 minus will give us the fraction that is explained by the model. And so we will get 1 if the model is perfect, and 0 if the model is trivial. So let's try this out. In that cell in column N, we are doing the calculation 1 minus L13, which is the SSE, divided by G13, which is the variance. So the units again cancel, so this is pure number, and we get this number 0.856, and we see that that is exactly the r squared. So now we've determined how Excel calculates the r squared value. The only problem remaining is for us to determine how Excel determined the y-intercept of the plot of the fit for the original data. Recall that we had shifted the x data by x average and the y data by the y average, or in other words, we worked with the deviations, and then that step eliminated the y-intercept of the fit line. the fit line of the two graphs had the same slope, had the same r squared, but had different intercepts, and the intercept of the shifted data was 0. This means that the origin is on the line, is part of the line in the shifted data. And since we shifted by x average and y average, that means that the point x average, y average is on the original fit line. So we have our equation for the line y equals mx plus b. We know the parameter m. We are looking for the parameter b, and x and y are points on the line. We know the point x average, y average is on the line, so we can substitute that point in, giving us y average equals the slope m times x average plus b. We can then solve this for b. B equals y average minus the slope m times x average, and we know all those numbers, or can get them easily enough in Excel, and so then we can recover how Excel determines the y-intercept of the original data.